When you've completed this lesson, you'll be able to convert back and forth between radians and degrees. Those are angle measures in 2 dimensions. You'll also be able to calculate partial solid angles, which are angle measures in 3 dimensions. Photonics technicians use angles in degrees and radians to make their calculations and their measurements. And so you'll need to be able to convert between those 2 measurements. You'll note that 360 degrees is equal to 2 pi radians, and we'll work with that a lot in this module. You'll also calculate partial solid angles, angles that are measured in 3 dimensions, such as the solid angle that is subtended by a beam of light that emanates out from a point source. It spreads out, and the volume and the space that encompasses is the measure of the solid angle of that beam. Here's an example scenario that photonics technicians have to work with. Laser light of 1.06 microns exits a laser through an aperture of 1 millimeter diameter. The beam spread of the light is through a circular opening of diameter d and is given by the equation theta equals 1.27 times lambda over d, where theta is the beam spread angle, also called the divergence. And that's given usually in radian measure. So we need to find the beam spread angle in both radians and the more familiar degrees. Well, to do that, we'll have to learn a little bit more about angle measure, and so let's go and do that, and we'll come back and solve this problem in a minute. Well, you've seen angles in triangles before, like 60, 90, and 45 degree measures. These are all based on 360 degrees in a circle. Another common unit for angle measure is the radian, and that's based on the circumference of a circle. You remember what the formula for the circumference of a circle is? It's pi d, or 2 pi r. 2 pi r is usually the more common mathematical way to do it because r is used a lot in the mathematics world. But you'll see that we have corresponding to 45 degrees, the measure would be pi over 4, or 1/4 pi. Because corresponding to 90 degrees is pi over 2. Corresponding to 180 degrees is pi radians. Corresponding to 360 degrees is 2 pi radians. Just remember this, that a full circle has 2 pi radians in it. Now, how do you convert between degrees and radians? Well, first of all, recall the value for pi is 3.1415926, and on it goes and goes. But we always just refer to it usually as 3.14 because 3 significant digits is usually enough. But here, it's more common when measuring angles to refer to it simply as pi. You don't even need to know the number, the value for pi. Just need to know that it's pi. Since 360 degrees is equal to 2 pi radians, or 180 degrees equals pi radians, we can use a unit ratio to convert degrees to and from radians, just like you've used unit ratios to convert millimeters to centimeters and miles to feet and so on. For example, let's convert 45 degrees to radians. Well, we use 180 degrees equals pi radians to form a unit ratio. We multiply by that ratio, pull out the values, and separate the units. The degrees will cancel, leaving us with just radians. And notice that we've not put in the value for pi, but left it as the symbol pi. So we have 45 over 180 pi, or more simply reduced to 1/4 pi. Example 2 says, let's go the other way. Convert 3 pi over 2 radians, or 3/2 pi radians, to degrees. Again, we'll simply multiply by the correct unit ratio and cancel the unwanted units. In this case, you'll notice that we put the degrees on the top and the radians on the bottom because we want radians to cancel. And so they group the values together, and this time the pi's will cancel. We'll have 3 times 180 over 2 degrees, which is equal to 270 degrees. Now let's look at solid angles, probably something that's new to you. Recall that two rays on a plane define a plane angle. You may have seen that in the previous module. The plane angle is the region on the plane that's enclosed by those two rays. So the angle measure is a measure of how far spread apart these two rays are. A cone in space is what's used to define a solid angle. So you can imagine this being a sphere, and out from the center of the sphere comes this cone. And how big the cone is, or how much space is inside the cone, tells us what the measure of omega, the capital omega, is the symbol that's often used for the measure of the solid angle. Now, a point that radiates in all directions, if we wanted to measure the solid angle of a point source of light or a radio beacon or something that radiates in every direction, then it would cover a total solid angle of 4 pi steradians. So in other words, if we weren't dealing with just a cone here, but if we took the cone away and said the light could go anywhere around, anywhere, all the way front and back and side to side, then the solid angle that corresponds to that would be 4 pi steradians. So the formula for doing that is that the solid angle is equal to the area of the sphere, of the part of the sphere that's intercepted there, divided by the radius squared, or how far away it is from the source. So that would be A over R squared. So for example, the solid angle defined by a whole sphere. We just figured out what that was in the previous slide, right? So if we had the whole sphere, well, what's the area of a sphere? That is 4 pi times R squared, right? So the R squares will cancel, and sure enough, the solid angle by a sphere is 4 pi steradians, just as it should be. So if we have something less than the sphere, then we'll be able to calculate the solid angle for that. So here's an example of determining the solid angle for less than a sphere. We have a point source of light that is 2 meters away from your eye, and we'll assume your eye has a radius of 7 millimeters. The solid angle formed by the light entering your eye, that's what we'd like to find. So we've got a cone coming out from that light source, and when it reaches your eye, we're only interested in the 7 millimeter radius circle of the light that's going to actually enter the pupil of your eye. All the rest of the light out here and all around is not going to go into your eye. Only the light that comes right from that source and down that cone all the way to your eye. So what we'd like to find out is what is the solid angle represented by that cone. That would be pi times the radius squared divided by the distance squared. You'll notice that we had to convert them to constant units. We converted them both to millimeters. And the calculation is 3.85 times 10 to the minus 5 steradians. So your eye intercepts only about 4 times 10 to the minus 5 steradians. That's not very much. That's only about 0.003% of all of the 4 pi steradians that are out there. So you can see that not very much of that light's actually entering your eye. Now we're ready to look at that solution to the example scenario. So we have laser light of wavelength 1.06 microns going through an aperture of diameter 1 millimeter, and we're asked to calculate what is the beam spread angle, what is the divergence, using this formula, 1.27 times lambda over d, and that will give us a measure in radians. So if we substitute in theta equals 1.27 lambda over d, put in lambda, we'll convert everything to meters so that we don't get confused about the microns and the millimeters. We know that 1.06 microns is the same as 1.06 10 to the minus 6 meters, and 1 millimeter is 1 times 10 to the minus 3 meters. So that way the meters will cancel, and we'll have two numbers to divide and multiply times 1.27, and the result is 0.00135 radians. Well, we don't have a very good feel for radians, so let's convert that to degrees. So we again multiply our measure of radians by a unit ratio of 180 divided by pi radians. The radians will cancel, and the result of the math will be 0.077 degrees. Well, that's a pretty small number. So that laser beam is diverging less than 1/10 of a degree. Compare that to a flashlight, for example. Now let's look at the practice exercises in this unit. How many degrees are in a circle? Well, you should have that right under your hat now, right? As you've seen, there are 360 degrees in a circle. We just want to be sure that you know that fact. Now, if a pi is cut in half across the diameter, and then each of those pieces is cut in half, and each of those pieces is cut in half again, how many pieces do we have? And how many degrees are in each piece? Well, it's pretty easy to see that there's 8 pieces here. And so if we have 360 degrees is all of them, and then you divide by 8, then each one must be 45 degrees. How many degrees are there between the 12 numbers on the face of a clock? Or between each of the 12 numbers on the face of the clock is what we'll ask. As before, we know that we've got 360 degrees in the whole clock. But this time, instead of dividing it into 8 parts, we're dividing it into 12 equal parts. And just one of those would be 360 degrees divided by 12, which would be 30. Now, how many degrees are there between 12 and 3? You can see that just by looking at it, can't you? But just to be mathematical about it, since one of those numbers is 30 degrees, and 3 of those numbers would be 3 times 30, or 90 degrees. Between 12 and 6, well, you can see that also without using any calculator. It's a straight angle, right? So that would be 180 degrees. But we can also do the math approach and say there's 6 numbers times 30 degrees per each number, and that would give us also 180 degrees. How about between 12 and 9? Now, this one you may not have noticed before, but this was 9 numbers times 30 degrees, which would be 270 degrees. And if they went all the way around to 12, from one end to the other, we would go around 360 degrees. So, and you could measure the angle for any one of those numbers and calculate that as well. So we just did it for a few of them in this practice exercise. Now let's convert 60 degrees to radians. So again, we're going to take 60 and multiply it times our unit ratio of pi radians over 180 degrees. We put 180 degrees on the denominator so that these two units will cancel. So then we group the values together. We have 60 over 180 pi, and we notice, sure enough, the degrees cancel, and we have radians as our result. And so the numbers will simplify to 1/3 pi, or 0.33333 pi. Now we're asked in exercise 5 to convert 5 pi over 4 radians to degrees. So we again multiply by the correct unit ratio. You'll notice it's a different unit ratio than the one up here because we want radians to cancel this time to result in degrees. So again, we group the numbers. The pi's cancel here and the radians cancel here, and we're left with numbers of degrees, which is 225 degrees. Exercise 6 asks us to calculate the solid angle intercepted by a little rectangular mirror, 4 centimeters by 6 centimeters, that is 1.5 meters away from a lamp. So this is pretty much like the eye problem we had in the text, right? So here we have the formula omega, or the solid angle, is equal to A over R squared, where now A is going to be the length times the width of that mirror in order to calculate the area of that mirror. And R is how far away the mirror is from the lamp. So we simply substitute in our expressions. A is L times W, which is going to be 4 centimeters times 6 centimeters. And instead of 1.5 meters, we'll, in our head, convert that to 150 centimeters so that the centimeters will nicely cancel for us. 4 times 6 divided by 150 squared. And the answer is 0.00107 steradians. So the mirror intercepts about 1 millisteradian out of all of the 4 pi steradians that are available coming from that lamp, or in other words, about 0.08% of the light emanating from the point source. It's always interesting to find out what percentage you're intercepting in that solid angle. All right, well, that concludes Module 9, Angle Measures in 2 and 3 Dimensions. I trust that you'll feel a lot more confident now about working with angles, measures in radians and degrees and steradians. See you next time.